Hi guys, and welcome to your second lesson in Unit 5. For today we're going to talk about how to do calculations involving buffer solutions. So, didn't put my face in this one because I'm going to be doing a lot of writing on the tablet. So sorry for those of you who will be disappointed that you don't get to look at my weird facial expressions. You'll be okay. Okay, so as we know from what we've learned so far, a buffer is a combination of a weak acid-base conjugate pair. So here we have a weak acid with its conjugate base. So I have 0.1 molar of each of them. So the old way of working pH problems, we would set up an ice chart. The only difference is that we have a starting amount for a product, which is unlike what we did in the past. But we're going to work it the same way, minus x plus x plus x. So I get the initial minus x, x, and the initial plus x. So then I'm going to set that equal to Ka. Okay, so Ka is equal to all of my equilibrium concentrations, products over reactants. It's the same as always, what we've done before. Now, because this Ka is so small, I can ignore these changes in x, which leaves me with 0.1 times x over 0.1 equal to Ka. So x is equal to 1.8 times 10 to the negative 5. Taking the negative log, I get a pH of 4.74. So if you did your POGIL, which you should have, this was the way that we worked the 4 buffer calculations on the POGIL. But then we have a different way that we can do for buffers. So if you are interested, if you're a math person, you can see how we derive this Henderson-Hasselbalch equation, how we go from the Ka expression, rearranging it to make Henderson-Hasselbalch. That's not something you need to know, but if you're interested, it's there for you. Regardless, at the end of the day, we get this equation that we can use to calculate the pH of buffer solutions. So you can only use this for buffer solutions, okay? We have pH is equal to the pKa, which we've done this. pKa is just the negative log of Ka. And then plus the log of the concentration of the base over the acid. So the way it's written is it's the conjugate base over the acid. But we can just think about this as base over acid. All right, so for pH calculations, pH is equal to the pKa plus the log of concentration of the base over the acid. And this is given to you on your reference sheet. Okay. So let's look at the same problem from the slide before. We have a buffer solution, 0.1 molar acetic acid, 0.1 molar sodium acetate. But this time, I'm going to use the Henderson-Hasselbalch equation to do it. So I'm going to plug in pH equals the negative log of Ka, because that's my pKa, plus the log of, this is my base, and this is my acid. So in this case, they were the same, so 0.1 over 0.1. I get pH equals 4.74 plus the log of 0, or excuse me, the log of 1, which is 0. That's a typo. The log of 1, which is 0. So I get 4.74, which this is a screenshot from the earlier one. We get the exact same pH. So whether you work it with an ice chart or with the Henderson-Hasselbalch equation, you get the exact same pH. So what makes a good buffer? How do we select what to use to make the buffer? So the very first thing is that the conjugate acid-base pair should have a Ka close to the desired pH. So we want a Ka close to the desired pH. That's the first thing. So look at this example. If I want a buffer with a pH of 4.5, I'm given these 3 options in order, being told, okay, I can use these 3 pairs to make my buffer. What I need to do then is determine what the pKa of each of them are. Remember, for a buffer, pH equals the pKa plus the log of that ratio. So if these are equal, that goes away, and pH equals pKa. So I need something that's close. The pKa is close to the desired pH. So the pKa of this first one is 1.92. The second one is 4.74. And the last one is 9.40. So we can clearly see that the acetic acid and acetate combination is going to get me a pH closest to 4.5. If I want to know the exact amount that I would need to add of each in order to get exactly 4.74, I can use the Henderson-Hasselbalch equation. So if, again, I reiterate, if the pH equals pKa, then, I just know that the acid and the conjugate need to be equal. But when they're not equal, I can use the Henderson-Hasselbalch to figure out how much of those I would need. So I'm trying to get a pH of 4.5, pKa 4.74, plus the log of base over acid. Okay, so when I solve this, I get negative 0.24 equals the log So that means my ratio of A minus over HA equals 10 to the negative 0.24, 0.575. So another way to say is that my base to acid ratio needs to be 0.575 to 1. So if I had 1 molar acid, I would need 0.575 molar of my base. What I need is that I need this right here to equal 0.75, because then the log of 0.75 is negative 0.24, which is going to correct this pH to give me 4.5. Also, a buffer is the most effective when the conjugate acid-base pair are in equal concentration. So I mentioned this before on the previous slide. If these are in equal concentrations, for example, 0.5 over 0.5, we get the log of 1, which is 0. So pH then equals pKa. So if I choose an acid-base pair that has a pKa very close to the pH I want, then it's going to be the most beneficial for these to be in equal concentrations, because my pH will then equal my pKa. And then finally, this seems pretty intuitive. Weak acids with their salts are better to keep pHs below 7, so that would be this part of the chart, while bases and their salts are better for a buffer over 7, so that would be this part of the chart. And even though these are written in terms of Ka and pKa, once we flip here, we notice that the Kb is going to end up being bigger, and that's what creates a basic pKa, which again, pH equals pKa when the concentrations are equal. So these would give me basic pHs, while these up here would give me acidic pHs. So let's do a couple just easy buffer calculations. So first thing we need to do is determine, is this an acid with its conjugate or a base with its conjugate? Because that will help us to fill in the Henderson-Hasselbalch equation. And so what I see here is I have an acid with its conjugate base, because I have the anion left over when this gets rid of a hydrogen. Okay? So now that I know that, So is this an acid or a base with its conjugate? It's an acid. If I need to, if the question asks me, I can write the equilibrium reaction. So I've got plus water makes CO2 minus plus H3O plus. And now it's asking for the pH. This is a buffer. So 0.2, whoops, sorry, the acid is 0.25 molar, base is 0.20 molar. So now my third step is to plug it in to the Henderson-Hasselbalch equation. So pH equals the negative log of the Ka, i.e. the pKa, plus the log of, it's always base over acid. So in this case, that's why we identified what this was. This is my base, this is my acid. So 0.20 over 0.25. And I get that the pH is equal to 4.64. Another easy example. This time, acid or a base, I figure out this is a base with its conjugate acid. I can tell because I have the cation of the base when it accepts a hydrogen. So this is a basic buffer. So if I need to, I can write out my equation. Notice I always just leave out my spectator ion because it's not going to do anything. Okay, now my last step is going to be the same. I'm going to plug it into the Henderson-Hasselbalch equation. But the issue here is the Henderson-Hasselbalch asked me for pKa, right? Well, I have Kb, which would allow me to calculate pKb. So if I have a basic buffer, I have to calculate Ka from Kb first. So I do that by doing Kw divided by the Kb that it gave me. And that equals 2.28 times 10 to the negative 11. It makes sense that the Ka is really, really small because this is a basic buffer. Okay, so now I can plug into Henderson-Hasselbalch. pH equals negative log 2.28 times 10 to the negative 11 plus the log of, remember, it's base over acid. This is my base and this is my acid. So the concentration of my base is 0.125 over the concentration of my acid, which is 0.130. Get the pH 10.62. Again, this is to be expected because it is a basic buffer. So those two were pretty simple buffer calculations. I didn't even have to worry about volume change because it just straight up gave me my concentrations. If I had to add the two solutions together, I would take care of my volume change and then I would plug it into the Henderson-Hasselbalch equation. So this question has us creating a buffer not by adding the weak acid or base with its conjugate salt, but by indirectly creating it by adding a weak acid with a limiting amount of strong base in order to neutralize a portion of it and create the conjugate. So in a problem like this, the first thing I need to do is find I'm going to find the moles of each because I'm adding two things together, so my volume is going to change. So for acetic acid, 0.1 liters times 2 molar equals 0.2 moles. And for sodium hydroxide, which we can just drop that sodium, I have 0.1 liters times 1 molar equals 0.1 moles. Then I'm going to neutralize with my strong base. So HC, so acetic acid plus hydroxide is going to create my acetate ion plus water. That's my neutralization reaction. I have my weak acid plus a strong base. Okay, so I'm now going to do the reaction. So I have 2 moles of this, and I have 1 mole of this. Clearly, I'm going to run out of the hydroxide. I don't worry about water. So now I'm left with 0.1 moles, 0, and 0.1 mole. So now I'm going to divide by volume to get the concentration. So my new volume is 0.1 liters plus 0.1 liters equals 0.2 liters. So I'm going to divide by 0.2 liters, which gives me 0.5 molar for both of them. So finally, my last step, I'm going to plug into my Henderson-Hasselbalch equation. pH is equal to the pKa, the negative log of 1.8 times 10 to the negative 5, plus the log of 0.5 over 0.5. You can plug this in your calculator, but you can see that the pH is going to straight equal the pKa. Like you could plug in log of 0.5 over 0.5, you're going to get 0. So I'm going to take the negative log of 1.8 times 10 to the negative 5, and I get 4.67 is my pH. So the only difference in that question and the ones prior is this time I had to create my buffer solution by neutralizing with the strong base. So I had that indirect way of creating a buffer where I neutralized part of the weak acid with a limiting amount of strong base. Okay, the last type of problem we're going to learn how to do is we are going to learn how to calculate the pH of a buffer after we add in a small amount of strong acid or strong base. So in this question, it's telling me that I'm adding 0.01 liters of 0.5 molar hydrochloric acid to 0.2 liters of the buffer prepared in the previous slide. So the buffer prepared in this previous slide was 0.5 molar acetic acid and 0.5 molar acetate. And if you recall, we formed that buffer by neutralizing half of the acetic acid with hydroxide to form the acetate. But in the end, we ended up with half a molar of each. So now I want to know what's the pH going to be after I add in this little bit of hydrochloric acid. So the first thing I got to do is find the moles of each. So I have for hydrochloric acid, which I can just call H plus because the Cl is not going to do anything. I have 0.5 molar times 0.01 liters, which gives me 0.005 moles. And then for both of the other two, I have 0.5 molar times 0.2 liters, 0.1 moles. So what I did is I multiplied the molarity times the volume of each piece of this puzzle to get the moles of each part. So now I got to neutralize, because that's what buffers do. We added this little bit of H plus and we need to neutralize that. So what reaction is going to occur? I'm going to have the acetate, or excuse me, that's not acetate. The hydrogen is going to react with the acetate ion because it is the base in that buffer to form acetic acid. Well, let me take what I got here and plug them in as my initial amount of moles. So 0.005, 0.1, and 0.1. Obviously, the hydrogen is in the limiting amount. If it wasn't limiting, then we would go over our buffer capacity. I'm going to be left with no hydrogen, which is what I needed because I needed to get rid of that addition so that my pH stays pretty much the same. And then here I'm going to have 0.095 and 0.105. So then I'm going to divide by volume so that I change this into molarity. My new volume is 0.2 liters plus 0.01, so 0.21 liters. So now I have 0.452 molar. And 0.5. So those are my new concentrations of acetate and acetic acid. So now I can just plug those into Henderson-Hasselbalch. So pH equals pKa. I have the Ka value of acetic acid. It was on the previous slide, so you would have it if you were working this problem. My base in this case is 0.452. Sorry, on my work, I have it written two different ways. Transposed number. I gotta figure out which one's right. Okay, 0.452 is right. Over my acid, and I get 4.70. And if we compare that before, from the previous slide, before we added the hydrochloric acid, the pH equaled 4.74. So we only changed by 0.04. So we definitely kept our pH relatively constant. All right, let's do one more. So a buffer solution is prepared from equal volumes of 0.2 molar acetic acid and 0.6 molar sodium acetate. So again, we have that same Ka of acetic acid, 1.8 times 10 to the negative 5. So my first question says, what is the pH of the solution? Well, because this is equal volumes, when I add, so it doesn't matter what volume you choose. If you said 100 of each, then together they're going to be 200. 50 of each, together they're going to be 100. Either way, when we add them both together, my volume doubles, so my molarity is cut in half. Right? Because, like, if I have 0.6 molar times 0.1 liters, 0.06. And then if it was equimolar, so now it has to be over 0.2 liters, well, now I have 0.3 molars. It's going to go in half. So for the pH of the solution, I'm going to do the Henderson-Hasselbalch equation. pH equals pKa Now my base is the acetate, so I got to take half of this, so 0.3, over my acid, I'm going to take half of that, which is 0.1. And I get 5.22, which is, of course, acidic. Part C says, what is the pH of a solution that results when 3 milliliters of 0.034 molar hydrochloric acid is added to 0.2 liters of the original buffer? So just like we did before, first thing I'm going to do is find the moles of each. So I have 0.003 liters. This is for H+. So remember, chlorine is neutral. It's not going to do anything. It's a spectator. So I have 0.034 molar times 0.003 liters is equal to 1.02 times 10 to the negative 4. So sometimes these numbers end up being really tiny, so we've got to use quite a few decimal places. Okay, and then it says we're adding it to the original buffer. So if I go back to the previous slide, which I can't do right now while I'm recording this, but you could look back at your work. Well, the ending concentrations that we had for acetate, it was 0.3 molar, and for the acetic acid, it was 0.1 molar, and it tells me we're adding 0.2 liters of it. So I get 0.06 moles and 0.02 moles. So then I'm going to do my neutralization. So what's going to react? Well, this is an acid, so it's going to react with the base. I have 1.02 times 10 to the negative 4 moles of the acid. I have 0.06 moles of the base and 0.02 moles of acetic acid. So minus 1.02 times 10 to the negative 4 plus 1.02 times 10 to the negative 4 leaves me with 0.0599, 0, and 0.0201. So I got to go out to quite a few decimal places. I'm dealing with such small numbers. So then step 3, divide by volume to get concentration. So my new volume is 3 milliliters plus 0.2 liters. 0.03 liters plus 0.2 liters give me 0.203. 0.295 molar and 0.099. So those are my new concentrations of acetate, the base, and acetic acid, which is the acid. So then step 4, I plug it in. Again, we're given this Ka value on the previous slide. Oops. Plus the log of base, which is acetate, so 0.295 over acid, which is 0.099. And I get that the pH is equal to 5.22, which is exactly what I got on the last page, or on the last slide. So this buffer definitely kept my pH the